In this part of the data structure course related to complexity of algorithms, you will learn how to calculate the asymptotic upper bound, asymptotic lower bound, and tight bound complexities for recursive algorithms. This example shows how to calculate the complexity of a recursive program. Here we have a recursive function factorial. We have parameter integer n and it returns the result, which is an integer value. If n is equal to 0, return 1. This is the constant case, else return n multiplied by factorial n minus 1. And this is the recursive case of the function. We are assuming that the complexity is Tn. This is a function of n. We are trying to find out what is this function. And here notice that if as part is chosen, there is a comparison here and as part is chosen. It is required in a constant time, and furthermore it will multiply with n and it will return it. This is required in constant time. And here we have factorial n minus 1. If the complexity for factorial with parameter n is Tn, we can replace this part with complexity Tn minus 1 because the parameter is n minus 1, plus we have some constant time required for this comparison and then as part, and also there is a multiplication here and also there is return, it is required in constant time. However, if n is equal to 0, it will return 1 and it is requiring a constant time. So we can write a recurrence relation for the time complexity. Tn is theta 1. If n is 0, it is this part. However, it is Tn minus 1 plus theta 1 when n is greater than equal to 1. After writing this recurrence relation, then we have to find out what is Tn. First, by using the recurrence relation, let's write Tn as Tn minus 1 plus theta 1. Then replace this Tn minus 1 with Tn minus 2 plus theta 1. We have another theta 1 here, so we will have 2 theta 1, Tn minus 2 plus 2 theta 1, and continue in this manner until we have T0 here. In that case, we will have n times theta 1 as the second term. And because the complexity for T0 is constant, because of that, if we consider the whole complexity, it is theta n. In this part, we are going to consider two different implementations of the Fibonacci numbers, and then we will find out what are the complexities. Remember that Fibonacci numbers are defined as when n is equal to 0, the value of the Fibonacci number is 0. When n is equal to 1, it is 1. However, if n is greater than equal to 2, then Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. That is, Fibonacci 0 is 0, Fibonacci 1 is 1, then comes 0 plus 1 is equal to 1, Fibonacci 2 is equal to 1. Then 1 plus 1 is 2, this is the next Fibonacci number, 2 plus 1 is 3, and this goes in this manner, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc. First, we are considering the non-recursive program to compute Fibonacci numbers. The name of the function is Fibonacci. There is a single parameter, which is an integer. This is showing n, and we are going to calculate what is the Fibonacci n. It will return that value. We have two variables to keep the Fibonacci n minus 2 and Fibonacci n minus 1. These are called Prev2 and Prev1. They are initialized to -1 and 1 respectively. We have another variable which is called sum. This will keep the result for returning as the result of the Fibonacci number. Here there is a for loop. We are starting with integer I equal to 0 and it is repeated until I becomes more than n. Each time I is incremented. Sum is equal to Prev2 plus Prev1 as given here in the formula of the Fibonacci number. Fn is Fn minus 1 plus Fn minus 2. Then we are setting Prev2 to Prev1 and Prev1 to sum. This is repeated n times and then Fibonacci n is calculated. Then return sum. This is the result for Fibonacci n. So this is the end of the Fibonacci function. If you consider the complexity, here notice that this part has constant complexity. Also this return part has constant complexity. For the for loop, we have complexity order of n. Because of that, the complexity of the Fibonacci function given here, the non-recursive program is big O order of n, omega n, and theta n. Now we are considering the recursive program to compute Fibonacci numbers. Again, the name of the function is Fibonacci. We have parameter integer n, and also it will return an integer value. If n is equal to 0 or n is equal to 1, it will return value n as the value of the Fibonacci number, as it will find out what is the Fibonacci n minus 1 plus Fibonacci n minus 2, and this summation will be returned from the function. Remember that Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. We have to write the recurrence relation to find out the time complexity. Here is the recurrence relation. Notice that if n is less than 2, that is, if n is equal to 0 or n is equal to 1, it is simply returning the value of n. So this part has a constant complexity. Because of that, we have theta 1 here. For the case n is greater than equal to 2, the else part should be executed here. And there, the Fibonacci function is called with parameter n minus 1. And then it is again called with parameter value n minus 2. So we are writing the recurrence relation, the second part, as Tn minus 1, Tn minus 2, plus here there is summation and it will return also the sum of these two Fibonacci numbers. Because of that, additionally we have theta 1. After writing the recurrence relation, we have to find what is the upper bound. In order to calculate the upper bound, big O order, for Tn, instead of that, by using the recurrence relation, we are writing Tn minus 1, Tn minus 2, plus theta 1. We are considering this line, and we are writing there instead of Tn. We know that Tn minus 2 is less than Tn minus 1, so instead of that, if we write Tn minus 1, we know that this is less than equal to 2 times Tn minus 1, and then we have theta 1 here. If we replace this one, this part, with Tn minus 2, we have to write here 2 times Tn minus 2 plus, we have to write theta 1, and it is multiplied by 2, and when added to theta 1, we will have here 3 times theta 1. We can reorganize this expression as 2 to the power 2 times Tn minus 2 plus 2 to the power 2 minus 1. It makes 3. Here, theta 1. If we continue in this manner until here the parameter is 2, in this part we will have 2 to the power n minus 2, and for the second term we will have 2 to the power n minus 2 minus 1 times theta 1. And continue one more step. We will have 2 to the power n minus 1, and we will have t1 here, plus 2 to the power n minus 1 minus 1 theta 1. And then instead of t1, we can write theta 1. So it is 2 to the power n minus 1 theta 1. And also here we have 2 to the power n minus 1 theta 1. So if we consider this expression, this is Tn is in the order of 2 to the power n. So if we consider this expression, Tn is in the order of 2 to the power n. Notice that this is exponential. Therefore, instead of using upper bound, we have to find out what is the lower bound. That is, we have to find out what is omega complexity of Tn. Again, we are considering the recurrence relation and we are trying to find out what is the lower bound. We have to consider the cases n is even and also the case n is odd. For the even case, Tn is written as, by using the recurrence relation, Tn minus 1 plus Tn minus 2 plus theta 1. And we know that Tn minus 1 is greater than Tn minus 2. And instead of that, if we write 2 times Tn minus 2, and if we omit this theta, in that case, we can say that this is greater than equal to 2 times Tn minus 2. So we are starting with Tn, and then instead of this one, we are writing 2 times Tn minus 2. Each time by decreasing by 2. Then in the next step, we can write 2 to the power 2, Tn minus 4. And if we go in this manner up to T2, here we will have 2 to the power n minus 2 divided by 2. This is because each time we are decreasing by 2. So if we consider this one, because T2 is complexity of theta 1, it is omega 1 also. It is multiplied by this 2 to the power n minus 2 divided by 2. So it is in the omega order of 2 to the power n divided by 2. If we consider the case n is odd, again we start with Tn. Instead of that, we write Tn minus 1 plus Tn minus 2 plus theta 1 as given here. And we know that it is greater than equal to, as written here, Tn minus 2 multiplied by 2. And we go on in the same manner, but only the difference is that instead of T2, we will have T1 here because n is odd. Again, if we consider this expression, T1 is replaced by theta 1. So this is in the complexity of omega complexity of 2 to the power n divided by 2. So if you consider these two cases, even and odd cases, they are omega 2 to the power n divided by 2. So Tn is omega 2 to the power divided by 2. Notice that this is exponential. So although the function looks very elegant, it is not feasible. It's an infeasible implementation. In fact, the Fibonacci calculation is in the omega order of 3 divided by 2 to the power n. This is more strict omega expression. However, showing it requires more elaborate analysis. However, notice that even with this coarse analysis, we are able to show that the time requirement is exponential. The omega complexity is exponential. So the recursive implementation given here is infeasible.